V. God damn it. Someone's fucking screaming in my house for the football game. Hey, stop screaming! Stop screaming! Hey, engineering dynamics. This type of shit is fucking painful sometimes. I mean, it's just these problems can take a while. Now, those problems I'm gonna do, I'll be doing about 6 problems. This is 1, this is 2, 3, 4, 5, and 6. So I picked these certain problems for all because these are the problems I think if I was teaching the class, I would put on the tests. Now, this would be covering chapters 15 to 16 of engineering mechanics, and that book is by Hibbler, which is what most universities use. And the concepts that will be covered is the principle of work and energy, and everything in black that's what's going to be covered. Now, the notation used, if you're unfamiliar with the notation, big T will refer to as kinetic energy. The sum of U to 1 is the sum of non-kinetic energies from point 1 to 2. And US is the energy of a spring, UG is the gravitational potential energy. And these are all this is all the formulas you need. In this class, there's really not that many formulas you need. That's just really concept based. So you need to know when to use these formulas and recognize what type of problem it is. Now, truthfully, some of these problems can be done using different ways. So what I mean by that is you could often swap the principle of work and energy with the conservation of energy. And that's what's recommended most of the time because the conservation of energy is a lot easier to use and to find velocities rather than the principle of work and energy, because the principle of work and energy is a scalar equation where you need to note that this is originally came from a vector equation and there's originally directions to this, so this will only work in one direction. Right, so your axes matter. This one, your axes don't matter. It's purely just energy. Okay. Let's start number 1 here. So if you read the problem, you're going to see that we have this brick, right, and it's sliding from A to B. And the question wants us to find, I believe, the velocity at B, right? Determine the speed of the brick before it leaves the surface of B. So we got to find the velocity at B. And then it's going to fall off the roof, right? And then we need to find that distance that it travels in the air. So already we see that this will definitely involve, what's it called? Some kinematics in here. And if we think about it, what principle are we going to use? Well, I'm going to argue that we will use the conservation of energy principle or the principle of work and energy, right? Let's see. Okay. So how I start these problems is I just write down as many facts as I can. Oh, damn it. 1 second. Oh, God. Okay, I got to be careful with my hands. I accidentally just moved everything off my screen. Okay, so VA is our initial velocity of 5 meters a second. What else do we know? Okay, so the weight is 2. And it's not 5 meters a second, it's 5 feet a second. Let's label our units. So we're using American units, imperial units, not American units, called imperial. W, well, W is equal to 2 pounds. Okay, what else do we need to know? We want to find VB, and we also want to find distance D. Okay, and then let's write some things. Let's write our plan, our objective here, using, so I think we should use this. I think this will be easier than using this. So T1 plus U1 plus, not plus, is equal to T2 plus T2. So this formula right here is just saying the change in kinetic energy is equal to the change in potential energy. And the reason why we're going to use this is because, well, it's coming from, if we take this point B, to be our origin, just like this, go along with this. If we take point B to be our origin, well, then it's coming from 15 feet above, which that has potential energy, right? It's coming at 5 feet per second. Okay, so it has a kinetic energy and a potential energy right here at this point. then past that point, at this point exactly, well, it's going to have purely just kinetic energy and no potential energy. Okay, so let's put all the words into writing. I'm going to go with the blue font here. So I'm going to write T1 and U1 and T2 and U2 as their actual formulas now. So 1/2 VA squared plus MGH is equal to 1/2 MVB squared plus MGH. 2 and 1. Okay. Now earlier I said just imagine if this was our origin, right? Now you can always pick your origin, right? But we should think carefully about why we pick it. Okay, so if we pick, let's think here. If we pick B to be our origin, what happens? Okay, well then that means that there is no potential energy at B. So this is, cross that out. So we just get 1/2 MVA squared plus, and what's the height? MGH. For H1, let's just write H1 is 15 feet. That stands for feet. If you put that dash right there, it's feet. And this is equal to 1/2 MVB squared. And we could factor out the m's, so the m's can go away. And we just want VB. We just want this term alone by itself. So it becomes VB squared is equal to, if we times everything by 2 and divide by m, we get VA squared divided by, oh, not divided by m. We already divided everything by m. So don't worry about that. We get V squared plus GH. Then if we take the square root, then we can erase the square on the side. Okay, so look at that. I mean, we got a pretty nice thing already. This tells us a lot of information. And if you caught me right now, yes you did, I messed up. It's 2GH. We need to times everything by 2 to get rid of the 2 on the side. So 2 times 1/2 is 1. That's why it's just VA. And then 2GH, which is that. Okay, so now we can just put in values for this. And we could say, well, VB is equal to, okay, VA was 5, so that's 25. It's 5 squared is 25. And 2GH, this is 2 times 32.2. Because we're in imperial. And what's H? H is 15. Okay. And now I gotta find a calculator. Usually I don't use calculators. Yeah, found a calculator. So 2, okay, actually this is 64.4 times 15, damn it, 64.4 times 15 plus 25, square root all that. We get 31.48 feet a second. Okay, this is really nice. I mean, we literally found a answer to the question already. We got one more thing we need to find. We also need to find I'm going to call it VC, okay? And so there's 3 things we need to find. We found one, so we can cross that up. We just need distance D and VC, and then we're done. Okay. Unfortunately, I think the other stuff will be a lot harder. Okay, let's find that distance. Now we can just focus on, let me draw this better diagram. We can just go back to physics 1 and use kinematics from here. So at this point we have VB, and it's actually traveling at this angle. So let me make that angle more clear. That's an angle theta. Okay. And there's gravity acting on this, so it's falling down to Earth at a faster rate now. But since this is only a entry-level class. We do not have air friction, so we can assume VBX just to be Vx. So in other words, it's not going to slow down, right? The horizontal velocity at this point will be the same velocity at this point. Okay. However, the vertical velocity won't. Let's find that vertical velocity. Okay, we have 30. So we'll just write h2 is equal to 30 feet. And okay, now let's just find our velocity vector here, where it would be, well, first we need to find our angle. Okay, if theta, we write the triangle actually. So this is 5, 4, and 3. And if we're coming down, oh, that looked messy. We're coming down here. There's an angle that we're coming at, right? So you could find this angle. And we'll put it right here. Okay. So theta, actually, let's not even find theta. Let's just write cosine theta. Well, that's going to be 4 over 5. And sine theta is going to be 3 over 5. Okay. And then now we can use this stuff, multiply it by velocity, and then we could find Vx, and we could find Vy, where this is going to be 31.48, so I'll just write Vb cosine theta, and V, what else? Vb sine theta. And yeah, you can put your numbers in here right now if you wanted, but I'm just gonna keep it like that for now, okay? So we found Vx, we found Vy. Now, we still need D. Like, this doesn't really help us that much. We need D. Okay, but like I said earlier, we're not slowing down horizontally. So what we can do is we can write our most general form of velocity, which is velocity is equal to distance over time. And then we could write distance is equal to velocity times time. And then we could make this a little bit more specific by saying it's Vx times time. So we should try to find time now. If we can find time, then we can find distance, right? So let's find time. So let's go back a page and look. Okay, so we got this. We got these two kinematic equations. Well, actually, we got 3. Now, which ones do you think we should use? Okay, so we're given a change in height. We're given a initial velocity. I'm talking purely of downwards, by the way. So we have a change in height, we have initial velocity, and we have a gravity, which is acceleration. Okay, so we could find time using this equation. Let's do that. And I will do that over, oh, don't want to do that. So we'll write V, change in, sorry. Oh God, I literally have that formula tattooed on my heart, but since it was there, I just did that. Change in Y, which is equal to H, right? H2 specifically. It's equal to VOT, VOY, because we're only talking about the velocity in the Y direction, plus 1/2 AT squared. And now if we want to make this specific, we would say that VOY, and yeah, what I should have done here is I should have called this, instead of VY, I should call this VOY, because our velocity does change in the Y direction. So it's important to do little things like that and to be wary. So VOY, if we put it into here, it is VB sine theta times T minus gravity over 2 plus T squared. Okay, so now I'm actually going to put my numbers in here. But before I do that, let me just say that this is all equal to 30. So I'm going to put my numbers in here now, and then I'm going to use the quadratic formula to find t. So we'll see what this looks like. Okay, well, VB, God, hate calculators. So we'll type 31.48, because this is VB. So we're going to find this. So 31.48 times 0.6 is 18.88. So we get 18.89 T minus, okay, gravity is 32.2. Divide that by 2, it's 16.1. T squared is equal to 30. And I'm going to input this into my calculator and find the quadratic formula. Use the quadratic formula in my calculator. So negative 16.1, 18.89, and negative 30. Okay, I typed something in wrong. Let me pause for a second. Let me just rewrite this better. We get negative 16.1 t squared. Now, oh, okay, so see the problem is gravity is in the downwards direction, same as our velocity. So what we should actually say, this is plus, plus, and plus. Now for these examples, you're going to notice that I'm going to try to take as little cuts as possible, because I want you to learn with me and see those things, because these are important. So what we should actually do in the beginning of this problem, before this little section, is we should have said this is our positive and this is our negative direction. It's important to define your axes, just like I said earlier. It's important to define your origins. So yeah, now we can type this into the calculator and get a legitimate answer. 16.1, 18.89, and oh, typed it in wrong still. It's spotting out. 1, 18.9 minus 30. Okay, that was kind of embarrassing. I kept putting the minus sign instead of the negative sign on my calculator, so my calculator kept getting error. But don't worry, all the work is correct. So time is equal to about 0.9 seconds. Here we go. So now, oh yeah, we can already find D. So D is equal to, now what is Vx? Vx is this times this. So it'll be 0.9 times 31.48 times 0.8. That 0.8 comes from this 4/5. So 0.9 times 0.8 times 31.48 is 22.67 meters. Okay, not meters, not meters. 22.67 feet. There we go. Okay, good. Now we just have one more thing to find. Speed that it hits the ground. Okay, well, we have our, this velocity doesn't change. This, our vertical velocity, increases. So if we want to find the actual speed it hits the ground, we just got to find the norm of that velocity vector at the end point. Okay, well, now we can go back to this kinematic equation where I'm going to write Vy is equal to Voy plus At, which Voy is equal to this right here, which is 18.89, and gravity is plus 32.2, T is 0.9. Okay, let's find this now. 18.89. Oh my god. Plus 32.2 times 0.9. It's about 47.87 feet a second downwards. Okay, and now let's just take the norm of this and this right here, because remember, it's a vector. So if we want to find the speed, let's say that this is VC. It's Vy squared plus Vx squared, which is the same thing as 47.87 squared plus, what else? What else do we got here? Where was Vx? Vx is this right here. Okay. 31.48 times 0.8 is 25.184. Yeah, there we go. So now let's just type all this shit into the calculator. Okay. Final velocity is about 54.1 feet a second. And let's give this a direction. It's going like this. There we go. Well, this is all you need for this problem. It only asks 3 things, and that's it. Okay. So, dynamics again, right? Well, let's read the problem. Let's think about this problem before you even read it. It looks like we have a spring, and, well, obviously gravity and the weight of this block is going to compress the spring, and we're going to assume that this spring is going to pop this thing back, and it's going to follow this blue line path. And before we could even read the question, we can assume that, I'm guessing it wants us to find d, and the only way we're going to find d is by finding the velocity at point B, and then using kinematics to solve for that distance. Okay, now let's actually read the question. So we have a 10-pound block. It's compressed to 2 feet. It's connected to a spring, and that spring is compressed to 2 feet at A. Now, okay, nice to know that this is a smooth plane, so there's no friction. And again, we want to find this distance d. And yeah, that's it. That's all it wants us to find. Okay, so let me turn on my tablet and let's start this question. So usually when we do these questions, I like to write out all of the knowns. So the knowns in this case, wrong thing. The knowns in this case are what? Well, it gives us the compressed spring, which is one of the most important knowns. We'll write it as S is equal to 2 feet. Okay, and we'll write W is equal to 10. And again, this is all in imperial units. Yeah, that's all it really gives us. So if we think about this problem, there's energy at the spring, and then there's gravitational energy too, and then when it gets launched, there's going to be kinetic energy. So maybe we should use this formula, T1 plus U1 is equal to T2 plus U2. And if we use this formula, what do we get? Well, T1 would be the initial velocity, which is non-existent because it's at rest right now. And U1, if we take this as our point of origin, we don't really have to worry about gravity at this case because it's on the ground right now. But there is one energy here that is potential, and it's the potential spring energy, which we'll call Ug, which is 1/2 Ks squared. Okay, now at T2. Okay, now at T2, this is where we think. So it's going from here to here. So there will be kinetic energy, which is 1/2 nat K m VB squared. Okay, and then at this point U2, well, not that point U2. At U2 describes the energy at this point, all the potential energies at this point. Well, there's only going to be gravity at this point because it's no longer attached to the spring. So we'll write UG is equal to not 1/2. Why am I writing this formula all wrong? MGH. And my face is blocking. Okay, so we can see that H is equal to 3 in this case. And yeah, we could find this other stuff we know. Okay, so this is good. We could find VB already. So let's just rewrite this equation as 1/2 mvb squared. We want this by itself, so we're going to have this term minus here. So this is equal to 1/2 ks squared minus mgh. Okay, so if we want VB by itself, right? Let's write that VB is equal to ks squared minus 2mgh divided by m. Okay, and squared. Let me just write this nicer. Well, we can see that VB is equal to, we could just write this as ks squared over m minus 2gh. And let's think if I did that correctly. Okay, so here we go. Times everything by 2. Okay, that's correct. And divide everything by m. Okay, so this is our equation that we want. Now, let's think about this. Let's write it here. Well, we're actually not going to think about. We're just going to compute it because we actually need VB. So K, do they give us K? They do. K is right here. So 100. What's S squared? S squared would be 4. And this is all over some mass. And we don't have the mass value, but we can solve for the mass, where we see that weight is equal to mg. Therefore, m is equal to W over G, which is 10 divided by 32.2. Okay, so M is equal to, yes, I will type on my calculator like a little nerd, 0.311. Okay, so let's write that, 0.311, and minus 2 times 32.2 times the height, and the height is 3. Okay, now we should think, do we keep this minus sign and call gravity negative? And if we call gravity negative in this case, then this turns into a positive sign. Okay, so let's think about it this way. And we're going to keep this as a negative sign, and we'll see what happens. The reason why I say we'll see what happens is because if this number, like the way you can also think about it is, should VB be accelerating? Should the speed be pretty big, or should the speed be kind of small at this point, right? Well, we know that it's getting launched and that gravity's acting on it. So that's a little bit confusing, but let's just get this number first. This is 400 divided by let me do that, 400 divided by 0.311 minus 2 times 32.2 times 3. And all of that square rooted. Okay, so I get, well, 33.1 feet a second. And I think this number is about right? That would make sense, right? This is, it's a block being launched by a pretty strong spring, and it's only going up a short distance, really. It's not going up a super high distance, so it's not defying gravity for a long time, and it's really just being launched by a spring for up a hill for a really brief second, right? Because this is only 3 feet. Okay, now that is our velocity at B, but remember velocity is a vector, so it's shooting straight out here. Now, we do need to find the distance here. So let's think how we can do that. Well, we're going to have to use a little bit of trigonometry here. So 4, 3. Okay, well, let's do that. So we'll write the triangle, 4, 3, and theta. we could see that cosine theta, and this is 5. Like, I just know it's 5 because I've seen so many of these triangles. Okay. You could check it with Pythagoras there if you don't believe me. Well, cosine theta is equal to 4 over 5. And sine theta is equal to 3 over 5. Okay. So let's define VBX, which is equal to VX, and VBY, which is equal to VOY. And of course, there's a cosine theta here, and there's a sine theta here. Okay. And my bad. VB. Magnitude. Okay, now that is, like, this is the appropriate notation. Right. Okay, so let's do 33.1 times 0.8. That is 26.47. Okay. And what is this one? It'll be 33.1 times 0.6, which is 19.85. And I'm going to give these directions. This is going this way, and this is going up. So we should label our directions. Okay. So this part, kind of like the last problem. But now we need to do a little bit more. We actually need to apply the kinematics here. So we know our velocity in the x direction, and we want to find our distance traveled in the x direction. So I'm just going to draw a new picture. This is what's really happening. Let me draw a better picture and show you what. So it's actually being like this, right? Because remember, there's an initial angle, and I don't know why I gave it a random point of inflection. There we go. Okay, this is a really appropriate picture now. This is how it would actually look like. And or this is Vx, and this is Vy. It's not exactly Vy, it's Voy. And then right here at the max point would be Vy and Vx. Okay, so this is the accurate picture now. Okay. So if again we use our regular velocity equation, we just really think as simple as we can. We could see that our distance, so now we're starting right here. We want to know from here to here. Okay, well, our distance is equal to velocity x times time. Okay, that's useful. And what else? Well, we know at this point, right, everything comes down. So we could use the fact that we have a change in y of 3 feet. So we let this go as following. V squared is equal to VOY. Let's not use this one actually. Let's use a different kinematic equation. Why don't we use change in y is equal to VOY times t plus 1/2 at squared. So we'll use this equation. This is a much more easier equation. If we would have used the other equations, well, we would have had to do more solving, and it would have worked, but it just would have took more time. Okay, well, what is this actually equal to? Well, VOY is right here. So 19.85 times some time t. Now this is going up, right? This is going up. I mean, this one's going up, and this will be going down because the acceleration will be negative. So it's going to be 32.2 divided by 2, which is minus 16.1. And we have t squared here. And all of this is equal to 3. Okay, so if we use the quadratic formula, we can find t. Let me run it in my calculator. So I'm going to type in negative 16.1 for A, and I'm going to type in 19.85 positive for B, and I'll write minus 3 for, what's it called? Our vertical displacement. Okay, now this is how I always do this, right? Is I like to just put things in my calculator and see what happens. So we get t is equal to 0.76 and 1.056. And this is like definitely not true. How about this one? What does this tell us? Tells us we could have messed up somewhere, right? So I'm going to cross out both of these times. Now the reason why I wanted to do that again is just to show you that it's important to think logically about, is this positive or negative? So if we define this as negative and this as positive, then if we're going down, we should be displacing 3 units down. So it's actually going to be -3 on the side. So now if we write our quadratic equation as -16.1 t squared plus 19.85 plus 3, and now we put that into our quadratic formula. Let's see what we get. -16.1, 19.85, and 3. Okay. So we get negative 0.136, which is definitely not it. But we also get t is equal to 1.37 seconds. Okay, so, right, remember, it's important to understand your notation and what you define as positive and negative, because when you put it into these kinematic equations, this is where a lot of things can go wrong. Like, a lot of things can go wrong, and it's not just the algebra mistake. It's not just, oh, I forgot my negative sign. It's actually a pretty big conceptual mistake, and they lead to other mistakes. So again, right, remember your directions, what you assume, okay? And if you would have assumed downwards as positive and upwards as negative, this would have been left as +3, and then this would be positive, and then this would be negative. But we are calling upwards as positive, which is the usual convention. So this is what we get. T is actually equal to this, not this. Okay, so now that we got that, we could actually find distance d. D is equal to, okay, what's Vx? Vx is right here. 26.47 times 1.37. 1.37 times 26.47. We get 36.26. And that's feet. And it goes this direction. Okay, that's it. Okay, this next problem is gonna be where it's gonna start kind of getting conceptually harder, right? Now, real quick, just think about this, right? If anybody goes to the gym, they know that there's a lot of machines where it's like a cable pull down, right? And you pull down on a pulley, right? And you pull up a lot of weight. But if you were to actually try to, curl that weight or do whatever with that weight by yourself and without a pulley, it's always a lot harder. So pulleys, again, they make our life easier. That's why we have a pulley up here. Okay, well, in this case, let's actually think about this problem. What is it asking us? Well, it wants us to find the force exerted on this cable. So if we put a force on this cable and this thing goes to 6 meters a second, originally from rest, so it's now accelerating because we put a force on it, and this is a mass. Okay, so there's a force and a force, right? That makes sense. Okay, now the real question to ask yourself, does this box float up? Does it float up? Now, for our class, for dynamics, since it's a level 1, engineering class, I'm gonna make the bold assumption that it does not float up. I don't think they would give us something where it just, freaking floats up, because that would be really hard. So I'm gonna assume that it gets dragged on the ground. Oh, let's see. Let's see what happens. Okay. So, mass 75 kilograms again. Write down everything you know just to get as much credit as you can. V is equal to 0. And its speed, okay, VB is equal to 6 meters a second. And that's all we are given. find f. Okay, so I'm going to say that it will be useful to kind of draw this diagram as like that. So a triangle and another triangle in here. So let's break this big triangle up into two triangles. Okay, so we got this, and we'll call this point B, this is A, and this is C. Okay, now this is where it gets important. This part right here. This is what we don't really know. But we know this is 2 meters. We know that this is 6 meters. And we know that this is 6 meters. Okay. So if we're to think about total change in x, and total change in y, well then let's call this thing r. I'm going to use green, r. So then r is equal to the change in x squared plus the change in y squared, all square rooted, which as you guys can see is 6 plus 2, which is 8. 8 squared is 64. Okay. And what's the change in y? The change in y is 6. 6 squared is 36. Okay, then r is equal to 10. Okay, so r is equal to 10. That's good. What else can we do here? Okay, well, yeah, let's just pause for a second. Let's actually now reassess and think about, are we going to, what type of formula are we going to use here? I believe we're going to use the principle of work and energy. Now, let's write that down. Oh no, I just accidentally enlarged everything. Okay, let me not do that. T1 plus the sum of energies from 1 to 2. T2. Okay, well, T1, oh thank God, that's just 0. Alright. And now we're just solving for what? Oh, we know what T2 is. We know it, right? So now we just want to find what this is. What is this? We'll find out. Okay, so let's just write this. Okay, so for our triangle, we should now go back to our triangle and let's call this R2. Okay, and you're going to see why in a second, why I'm doing all this stuff. So R2, that is equal to 2 squared plus 6 squared, which is 4 plus 36, which is square root 40. We'll just leave it like that. You don't need to put the decimal. You don't need to type that in your calculator. You can do it later. Right? You don't need to do that now. And if you find things as decimals too early on, you'll lose points because you're going to keep getting more and more error in your answers. You don't want that. Okay, so we've defined this triangle for the most part. Now, what we need to really do is we need to find the change in S. Okay, what I mean by that is it goes, this is R1 and this is R2. So I think our change in S would describe R1 minus R2. Okay? Because the reason why we're doing that is because it's like this box, we know it just goes from here to here. So there is this change, but it's not just like, we are changing the X value here, right? It goes from 8 to 2 if you were taking this as your origin. But more importantly, this rope is changing. It's quite literally changing lengths, okay? It's going from R1 to R2. 10 minus square root 40 Okay, and now you can type this in your calculator. 10 minus square root 40. That is 3.675. Okay, now this part, like, this, you need to kind of think about it, right? Like I said, we had this big triangle, and we have this big triangle at rest. And then when a force gets pulled on it, everything moves. So then it kind of shifts into that smaller triangle. That's why I made an emphasis on this a little bit earlier. Okay, so we have our change in S. Now, okay, look at this. This box is not floating, right? I said it's not going to float. And there's no spring on it either. The only thing that's going to make this box move is force. Now, go back to physics 1 real quick and think about this. Work is equal to force dotted with distance. And that's if you write it as vectors. But you most likely see it as FD cosine theta. And in this case, we don't really need to worry about that cosine theta, so we can just write it as FD. And write these both as scalars, just indicate them as scalars. So that's what we're going to do. Okay, and what's another way of saying this? This is F times change in S. Oh, look at that. So this work is equal to this right here, okay? Remember, energy theorem, right? Work is equal to the change in energy. Now, it depends if this is like, so work is equal to the positive change in kinetic, but is equal to the negative change in potential. That's just something to remember, but we don't really need to think about that right now, so I'm going to erase it. Okay, so we know that this 1 minus 2 is equal to F change S, which is equal to 1/2 mvb squared. Okay, so again, what do we want here? We want to find this force. So we're going to isolate for force. We can get force is equal to 1/2 change in S mv. God damn it. Someone's fucking screaming in my house for the football game. Hey, stop screaming! Stop screaming! Okay, so this would be 2 times this. 2 times 3.675. And what is m? M is 75. And v squared, what? Oh, they gave it to us. Well, v is 6. 6 squared is 36. Now we can put this in our calculator, so let's write this. It's 36 times 75, and all of that is divided by 2 times 3.675, which is 367.35. And what type of units is this? This is all in SI, newtons. Let me not write that. That looks like a vector norm. You use parentheses, newtons. And maybe we indicate that it's going this way. There we go. All done. This next problem, let's let go. It's a chapter 15 problem. So this is impulse and momentum. So what's happening here? Well, we got 1, 2, 3, 4. We got 4 forces pulling this way. And we got a force pulling this way. So where's this thing going? Is it being pulled this way, or is it being pulled this way? We'll find out. Right? It's our job to find out. Okay. Well, we have the mass. Let's write down the mass. M is equal to 30 kg. Let's write down another constant. Okay. Oh, so the box, the block, it's moving to the left with the speed. So it is going this way. Nice, they tell us. Okay, it's moving to the left, which is equal to 5 meters a second. When F1 and F2 is acted on it. Okay. Now we just want to find, let's write this as V1. We want to find what V2 is equal to. Okay, and we want to find it when the change in time is equal to 6 seconds. Luckily, there's no friction, and we don't have to worry about the mass of the shit. Okay. Now, let's write down our formula first. This was not included in the front page, but you don't really need it because it's right in the front page because it's kind of just known, right? You know this. It's just you sometimes don't call it I. You had this on the front page. You just don't call it I. Okay. That's what it is. Impulse is equal to the force integrated over some time. And look at that, we're given these graphs. So if we take the integration of this, we can find the area under these curves. Now, if you were to actually go about this and set up like slopes for all this stuff, I would say you're wasting your time. What we should do is find the integration of this geometrically, right? Okay, so let's indicate that this is F1, I1, and we have I2, just integrated F2, D. Okay. So for F1, we have this whole square area under here, which is a length of 6 and a height of 10. So 6 times 10 is 60. And we have a triangle here, which is 2, and it goes up 20. So 20 times 2, 40, and since it's a triangle, 40 divided by 2 is 20. Okay, one more area to find. This box here, which is 2 by 20, which is 40. So 60 plus 20 plus 40, that is 120. That's good. I2, what's the second impulse? Don't want to do that. What is the second impulse? Let's compute this whole area under here. That's 4, and it goes from 40, so 4 times 40 is 160. And well, what do we have here? 2 times 40, no, 2 times 30, which is 60. 60 divided by 2, since it's a triangle, it's 30. And we have this little area under here, and that's 2 times 10, which is 20. Okay, so that is 190. 190 plus 20 is 210. Right, okay, there we go. Nearly done already, actually. That's what you need for the most part. Yeah. But we should notice that we had 4 F1s. So let's use a different pen, and we'll say 4. Okay. But we only had 1 F2, right? We only have 1 F2. But we have 4 of these guys. So we'll write in green now, which we'll write I2 is equal to 480. It's not I2, that's I1. My bad. I1 and I2 is equal to 210. And of course, these are vectors, right? They're going in different directions, so we should minus them. So 480 minus 210, that's going to be 270. Okay, and it's in the direction of wherever I1 is going. So let I1 be our unit vector. Describe this. Okay, so again, nearly done. Oh my god, I almost just threw something off. Damn it. Like, okay. So, okay, now we can actually start trying to solve our velocity here. So this is what I meant by you actually seen this equation before. It's mv1 plus the sum of the integrating forces, F dtt, is equal to mv2. Alright, here you go. That we just had to find this thing earlier. And this, why did I... This thing right here is this. Okay, and it's going in the direction of I1. And I1. So, oh my god, I'm messing everything up. Yeah, I messed everything. Sorry, like I'm accidentally enlarging things on my tablet, and then it's getting enlarged on your screen. Okay, let's solve for v2. v2 is equal to v1 plus, now, like I said, this right here is this. So it's plus 270 divided by m. Okay, now remember v1, this velocity, it's going to the left, right? So it's going negative, and what's m? M is 30, so it's negative 150. And this is just 270. Because now it's just purely a scalar, right? We're just input of the scalar. And what is m? M is 30. Okay, so 150, 270 minus 150, that is 70 minus 50 is 20, and 100, so it's 120 over 30. And that is equal to 4 feet a second. Okay, that is where v2 is going, and v2 is going that way, as indicated by 2. There we go. Now for this next problem, this is going to, in my opinion, be the hardest problem. And I wouldn't be surprised if this is literally the problem on our test, if you're going to the same university as me, right? This is an impact problem, and it's a kinematic problem, and it could be even a work and energy problem if you want to make it. There's a lot of ways to do this problem, but it's definitely an impact one. Okay, so baseball, right? Now think about this baseball. If you wanted to hit the ball as far as you wanted, you would use your bat, and you would try to keep your bat in contact with the ball and swing through all the way. Just like in golf, they always preach swing through, right? Swing through. Okay, that's what this baseball player is going to do. Now, the concept that you need to understand here is that this ball will ricochet. So v1 is the velocity coming in, right? As the velocity is 30 meters a second just before it hits the bat, and it's coming in at this. So since this is, like, I'm going to keep saying this, since this is just a level 1 engineering class, you're gonna assume that the velocity out of this is going to be exactly the same as into it, right? You're going to assume there's no loss, and that simply he's just magically maintaining the momentum of the ball and just redirecting it. Only because this is a level 1 engineering class, and if we were to give you more complications, like the force he actually hits the ball with, this problem would get really hard really fast. And I would say it would be unsolvable. For me, at least. Okay, let's write down our nouns again. M is equal to 0.15 kilograms. I don't know if that's a big baseball. I mean, I feel like that would be kind of big for a baseball. V is equal to 30. And let's write that as V1. Okay, and we need to find what V2 is. What else do we need to find? Determine the magnitude and the average impulse. So we need to find F average, which is equal to 1 divided by the change in time of the integral f dt. Okay, what else? Oh, well, we're given the change in time, which is 0.75 milliseconds. And I'll write that as 0.75 divided by 1,000, and that's a second. Just leave it like that for now, right? Okay. Oh, look at this. 100 meters, 2.5 meters. We're probably going to have to use that, so we might as well write it down too. Change in x is 100 meters. Change in y. Take this point to be your origin. Take the baseball point to be your origin, and their change in y would be 2.5 minus this. 2.5 minus this. So change in y is going to be 2.5 minus 0.75, which I believe is going to be 1.75. That is our change in y. Okay, so we got all that. That's a lot of information. How are we going to use that information? Let's go with this equation. M1 V1 M1 V1 plus the sum of the integration f dt is equal to mv2. Now, m2 and m1 are the same, so I'm actually going to erase the subscript. The ball does not change mass, so we don't need to differentiate our subscripts. Okay. Nope, I just accidentally enlarged everything. Nope, I accidentally shrunk everything. Okay, so I'm going to draw a new diagram real quick. So this is 15 degrees here and 15 degrees here. We're going to add those. That's just going to be 30 degrees. And this will be V2. So this V2 is him hitting the ball, right? V2 is him hitting the ball. So V2, we'll let Vx, and let's call it VOY. Vx be V2, V2, cosine 30, sine 30, which is equal to, what did he hit the ball at? He hit 30. Cosine 30 is square root 3 over 2. Sine, this is 30, 1/2. So this is 15, square root 3, and this is 15. Okay, so this is the velocity in the x direction that he hits the ball, and this velocity is positive, right? This is going up, so he hits the ball up for a bit, and then gravity is going to act on it. Let's give these directions and indicate what's positive and what's negative. So here's our directions for our velocity. Therefore, we have a speed, and we have a direction, so we have a velocity, right? Okay, so we're not done because we need to actually use that stuff. So Vx is equal to change in x divided by the change in time. Change in x. So then if we want to find, well, actually we know what change in x is and we know what the change in time is, so that wasn't that useful. Actually, this is change in times 2, not times 2. This is, yeah, we actually don't know what this change in time is. With this change in time is the time he hits the ball. So let's actually go back for a second and label hitting ball, and change into 2 is equal to the travel time. Yeah, I almost just made a big mistake there. I'm thinking that this time is this. That's not true. This is travel time. The ball's traveling. This is just when he hits the ball. So we want to find this change in times 2. Change time. I'm going to say this change in time. And for this, like whenever I write the subscript 2, I'm talking purely about the travel time. This is equal to the change in x divided by Vx. And our change in x is 100. And our Vx is 15 over square root 3. Okay. Well, this is important, and we'll just leave it like that for now. So we know our change in y, we know our change in time, but let's just call this, instead of saying change in time, let's just call it equal to t2. Okay. Now we want to know the impulsive force, the average impulsive force. Okay, so we want to know what this is, right? And that is equal to the integral, the 1 over the change in times of the contact time divided by f dt. Okay, well that's all true. What we really want to do is we can recall this the change in time. And remember f integral dt is the same thing as m vf, right? This is momentum. I mean, this is impulse, and the integral of f is impulse. Okay, so we need to find what vf is. Now vf is equal to the velocity at, I'm going to call this at the catch. At the catch. Okay. So, in other words, it is equal to v2x squared plus v2y squared. And note that I had v2 in here, so this is really v2x, and this is voy2, right? But you guys know that this is definitely not v1, so again, this is just kind of overkill right here, but we're not gonna not do it. Okay, well, we don't know what this is. We know what this is, but we don't know what this is. Okay, let's solve for it. Maybe we can use this kinematic equation, which we haven't seen for a while. It doesn't deserve, it usually doesn't get much attention. Okay, so we can use this one, because we got a time. It's right here. We know what gravity is, and we know what this is. So this would be like the simplest way to just define this velocity. Okay, so let's put in the values now. So it'd be 15 minus, okay, because we're assuming gravity is negative here in this case, because we are calling the positive direction up. So minus 9.81 times 100 divided by 15 square root 3. Okay, now that is time to actually use the calculator. 9.1 divided by 100 times 100 divided by 15 times square root 3. And 15 minus that. Okay, so I got negative 22.76 meters a second. So, you know, this makes sense, right? Because the ball should be coming down at his hand, right? Boom, hitting his hand, coming down. And it should be kind of slow at the second going down because it was nearly like the peak. This is the peak, right? So if it's at the peak here, the vertical velocity is 0. So now it's finally starting to regain its speed coming back down. Okay. So let's find what VF is as a scalar, right? Again, if we, okay, I already wrote the equation up there. I'm going to use that equation up there. It is this thing squared, which this is 15 squared times 3, plus this guy squared, negative 22.76 squared. Okay, so 225 times 3 minus, not minus, sorry, I'll tell you in a second. Let me just put it in this calculator. I hate calculators. Oh my god. Okay, I got 34.54 meters a second. You know, like, that's just a rant real quick. We shouldn't even be given these numbers, right? Like, I used to hate the fact that in like physics recitation they didn't give us numbers. And then now it's like, why are they giving us this stuff? This is just wasting our time. Like anybody can put this stuff in the calculator. But if they just gave us variables, it would save more time, and you wouldn't get graded on decimal places. Why are we being graded on decimal places? It's no skill. It's just purely who has a better calculator. Okay, so we have that. This is not really our answer. I mean, I don't think they really asked for that, but I'm gonna circle it anyway because it's accomplishment. What they wanted to find is this right here. So that right there is equal to 1 divided by 0.75, 10 to the third, divided by 10 to the third, all times 34.54. And I'm just going to raw put this in my calculator. 0.75 divided by 1000. 1 divided by that. And then times this. Okay. So I got 46052. Right. Now I'm going to admit my mistake real quick. It's a small one, but it's a mistake. This shouldn't be this. And what should this be? Right. I hope you saw it. It's not just VF, it's M times the change in velocity. Man, come on, how can you forget the change? The change in velocity is so important. It's not just one velocity, it's the change in velocity. Okay, so I made the cut, right? So remember, mass, change in time. I just re-inverted this because it was originally under. So it's the same thing here. And this is the mass. This is velocity final coming down. Speed final. Let me call it speed final. So it's really, we're using scalars here. And V1. So V1 is going this direction, right? So that's in the negative direction. So negative, negative, plus. Okay. So let's see what this would be. Okay. Well, I did type in my calculator earlier. 12,908 newtons, which you should write as 12.91 kilonewtons. Okay, now that is everything you want to know. That's what the question actually asked. So there's our final answer. This will be the final problem we do in this video. So we covered 6 problems for 2 sections, 3 problems, 3 problems. And if you know my class, you said the test would only be 2 to 3 problems. So we did good for this one video. I will probably make some more videos on some more problems, but I found that these problems were challenging, but weren't too time consuming and weren't impossible. But they're just a good challenge, you know. There'd be what I would call mild, moderate problems. Problems that would be on a test. Okay. Now, this is a problem that, so this block, it's going to slide down the hill, right? But we want to know that the direction it's going to slide, so theta 2, and we want to know what v2 is, but we're only given variables, so this is going to be fun. Now, we know that it's traveling with the initial velocity, and it will encounter some potential energy, so there will be kinetic and potential energy in this case. So let's state that we have T1 plus U1 is equal to T2 plus U2, where we could write T1 as 1/2 mv1 squared, and U1 would be mgh, and T2 would be 1/2 mv2 squared, and U2 would just be 0, right? We don't have to worry about this because at the bottom of the hill there's no potential energy. So we really just want to solve for just V2. So if we times this thing, if we times everything by 2 and divide by m, we'll get V1 squared plus 2gh, and we square root that, and all of that is simply equal to V2. So yeah, I mean that's one part of the problem. I mean, we did that pretty fast. That was the simple part. Now, actually finding the angle here is going to be what's the hard part. It's not really just trigonometry being in play, but there's a little bit more. Okay, so why is my tablet's freezing? Great. Okay, so we could write this diagram here. Now imagine if we try to just picture this, if we're just standing on top, like if we're a helicopter and we're flying on top of this hill, we could see that V1 is here and there's a theta. And then this translates into some V2 with a theta. So already we can see that there is this other vector here. Let me write this in a different color. Okay. Now, if we just think about it in this direction, right? Because like it's going down this hill, but it's pointing out this way. So really, it's pointing out this way, right? That makes sense. And since velocity is a vector, but we want to analyze with respect to an axis. So if we call the y-axis our fixed axis, right? If it's going straight this way, and then our velocity, if our block is sliding out this way, then we could find that angle right here by using sine. So simply v, actually, let me not write v. We're going to use the fact that the momentum here is the same as the momentum here. Right, that's the momentum theory. mv1 is equal to m2 v2. And m1 and m2 is the same thing. So let me actually just write this. Let me just erase the subscript for m, just to indicate that we're using the same. Okay, but more specifically, we could rewrite this as mv1 sine theta 1 is equal to mv2 sine theta 2. And remember, the sine theta is coming in here because we are concerned about the angle changing with respect to the y-axis. So this is the y-axis that's going this way, and the block is sliding out this way. So what is the angle changing? We can describe it using sine. Okay. So we actually know what theta 1 is. They declared that theta 1 is a known. So all we're actually solving for is theta 2, where we see that sine theta 2 is equal to mv1 sine theta 1 divided by mv2. The masses can go away. Well, that's nice. Okay, so we got this equation. But we don't know... Oh, well, we do know what v2 is. v2 is this. So this will expand into... And now I'm going to move myself over here. So it'll be v1 sine theta 1 is equal to v1 squared plus 2gh. So we have this answer that's purely just of v1. So this is an answer purely of just knowns, right? We don't have any unknowns in here. If we could have left v2 in here and then say comment to the reader, this is v2, right? Like it could be like a textbook. That's what textbooks do. They solve for something and then they relabel it and say, oh, go back to page 3. And that's what it is. But this is the answer, right? That's what we want. But not completely. We want theta 2 by itself. So theta 2 is equal to the sine inverse of all of that. So it's v1 sine theta 1 and square root v1 squared plus 2gh. So this is your final answer, and that concludes the video. Now, if you want me to do more problems, well, you need to like and subscribe. Right? I need to see that people actually are enjoying these videos. And if you have a certain problem you want me to do from the textbook, from the I think it's Drew Hibbler textbook, Engineering Dynamics, and between chapter 14 and 15, pick up a certain problem you want me to do, and I'll do it. Right? I'll do it. I might make a video doing an angular momentum problem, but I don't think angular momentum will be on our tests. But I might just release a separate video just for that. Consider subscribing and liking if you found this video interesting or helpful. Leave a comment. Just leave any comment, just so I could, get this video pushed up the algorithm.